Good afternoon, one and all. This is lecture number 10 in EHV, that is Electric and Hybrid Vehicle course. We are in the second module already. Today we are going to see the very important topic. First of its also, it is going to be a introductory session for electrical drives. Why electrical drives is required, where is it used, and what are the different types of electrical drives used in electrical vehicles. All those things we are going to see. We will start with the first type of drive, DC motor, and we are going to see the working principle of only DC motor. Obviously, in consequent classes, we are going to see the details of DC motor, how is it helping electric vehicle in propulsion and related things. So this is the outline of the second part of module 2. So first part was propulsion system. There we have seen SI engine, CI engine. We have seen turbine based propulsion system. This is the second part of module 2, where we are going to see electrical drives. First, in today's lecture, we will see what is the general configuration of electric vehicle. Then we will see what is DC motor drive, principle of operation only we will see today. In consequent lectures, we will see induction motor, brushless DC motor or drive, which is called as BLDC, and switched reluctance motor, which is called as SRM drive. Though I have mentioned here towards the top that your topic of DC motor operating principle is going to be your self-study topic, but anyways, I will do that as the topic for a regular topic, so it will not be left out. Okay, so let us go to the next slide and let us find out, excuse me, what is the electric propulsion system. So you can find it in the book of Ehsani. This is page number 139, module number 7. So modules are not exactly in order as per our syllabus is concerned in Ehsani book. Whenever we are saying electric propulsion system, that is in case of electric vehicle, they are the heart of the EVs or HEVs. There are three things you should remember. This can be asked as a short question. So there are mainly three parts of an electric propulsion system. First one is electric motor. Second one is a power converter, which falls in the domain of power electronics. And third one is electronic controller. So there are different type of controller: on-off controller, PID controller. They are very smart kind of controller. Model predictive control, adaptive control is highly used in all these vehicles. So electric motor, power converter, and controller. So controller is a part of your control systems. Motors, I think you have studied in first year. And power converters, a few people, if you have taken power electronics in the semester 5, maybe, or in this semester, I guess, I don't know. So that will be covered in power converters will be covered in power electronics. What is the electric motor? Electric motor converts the electric energy into mechanical energy to propel the vehicle. This system in vehicle enables the regenerative braking. So regenerative braking happens when we are using electrical braking, and it generates electricity for changing the onboard generates energy storage. So electrical braking actually enables regenerative braking, which gives some power back to the battery, and it helps save some energy in electric vehicle. A very important feature of electric vehicle which is not found in a mechanical vehicle. What is power converter? It is used to supply the electric motor with proper voltage and current. So very easy explanation is, if we are using induction motor for propulsion system, that means induction motor or AC motor, they are giving the power for propulsion, but we are generally storing energy in terms of DC energy, that is in the battery. So from DC we have to first convert the DC into AC. There we are using DC to AC converter, or it is called as an inverter. And then output of the inverter we are connecting to the input of the AC motor or induction motor. So there you need power converter. In this module only, we are going to see, maybe in the next lecture or so, there is something called as a DC chopper, or which is called as a DC to DC converter. So all these things are falling in the domain of power electronics. We will see DC to DC converter in this module itself. Third one is the electric controller. It commands the power converter by providing control signals to it, and then it controls the operation of the electric motor to produce proper torque and proper speed according to the command from the driver. Now, as it was discussed previously, command from the driver are three: brake, acceleration, and direction. So, whenever we are pressing accelerator more, that means we are asking vehicle to run with a faster speed or more acceleration. So, in that case, uh, the signal goes from the sensor, which senses that driver is asking for more power. That signal first goes to the ECU, that is electronic control unit. An electronic control unit, which is a microcontroller, very smart microcontroller, it will tell the whole power system that yes, more power is to be connected to the electric motor because driver is asking so. So in that case, power converter is going to change its input output configuration. Electronic controller will generate the control signal. It will control the power controller, power converter, so that more power from the battery will be taken and it will be channelized to the electric motor. So this is more or less the overall strategy or source to that wheel, whatever is the powertrain. So these are the main three electric components, that is motor, power converter, electronic controller. They are playing with the power part in EV. Electric control in vehicle. So what all things they do? So the electric controller can be further divided into three functional units. All this can be asked in the exam. These are very important slides, so prepare well. You will understand the fundamentals, but if you don't read it categorically, you won't be able to write in the exam. So what does a sensor do? So there are mainly three kind of things, three functional units. First one is a sensor. Second one is a interface circuitry, and the third one, which is a very important part, which is called as a the processor. Processor is nothing but the microcontroller. You are studying very different kinds of microcontrollers. The sensor is used to translate the measurable quantity. So it is sensing tire pressure, it is sensing how much is the accelerator is pressed, how much is the brake pressed. Whenever you are pressing the clutch, there is a sensor which is sensing that yes, clutch is pressed. Whenever you are putting the key in the ignition and you're trying to switch on the car, there are two, three different sensors which are sensing whether the key is inserted properly, whether the key is present for starting the car. So at every step there are sensors. So there are many sensors inside a vehicle, and you can find here the list is given, the quantities which are measured or which are tracked inside a vehicle are current, voltage, temperature, speed, torque, flux, that is magnetic flux. All these things related to different part of the vehicle, they are picked up and they are converted into all these quantities, and they are tracked by data acquisition system, and all this data are latched in the memory whatever is there, and microcontrollers actually pick up the data from those memories and it takes a decision accordingly. But one thing that these signals are very coarse, or they are not very polished kind of a signal. So every time we are capturing some signal, we have to uh, shape this, or we have to prepare the signal for proper recording, for proper storage, and also that is actually those circuits are called as signal conditioners or wave shaping circuits. So first is the sensor. This is picking up the signal which are not in very polished form, perfect form. So they are converted to a very proper signal by means of interface circuit. And whenever those things are very properly done, then the processor actually comes in the picture. So processor actually can see all the event happening. That is a very important thing. So processor output signals are usually amplified via the interface circuit to drive the power semiconductor device or power converters. So all these signals which are picked up so far, which are polished and shaped properly, they are stored in the memory or they are directly fed to the processor. And depending on that, processor comes to know that what the driver wants, what the how the car is behaving and all. And depending on that, the processor uh, gives or generates a control signal. That control signal goes to the controller, that okay, maybe brake has to be pressed, maybe accelerator has to be pressed. Whenever accelerator is pressed, it is requiring for more power from the motor and all those things. So those signals will be generated, and proper valve or proper actuator will be actuated, and the proper power will be supplied and things will be executed. So the functional block diagram for the overall electric propulsion system is given in this slide. So this diagram you might have to draw in the exam, and you have to explain. You can see here down there are mainly three blocks. So first block is the electronic controller, which is an embedded system. It's having a software, hardware. So hardware in controller is microprocessor, microcontroller, DSP, a transputer, and the different softwares, that is FOC. So this is field oriented control, MARC. So it is a kind of adaptive control unit. So STC, VSC, NNC, fuzzy. So these are variable voltage and frequency control, VVVF. So these are all different softwares or paradigms that we are finding here. And you're finding that all are connected to the transmission differential. So you're finding this is from transmission differential, the signal is coming back to the controller. From the tire wheel speed, it is coming back to the controller. Okay, so after controller, the signal goes to the power converter. So controller comes to know from different sensors that what actually is happening around the vehicle and what the driver wants to do, what kind of response the driver is expecting from the vehicle. Depending on that, controller takes decision, and it tells the power converter that yes, this much power is required, and this much power the power converter has to be supply. Accordingly, from the energy storage, power controller sucks the energy, because power converter is not a storage thing. So storage thing is power storage or energy storage, which is generally battery. From there, power converter sucks energy depending on the signal which is coming from the electric controller, and power converter then forwards that energy to the propulsion system, which is nothing but electric motor here. Now I told you, if it's a DC motor, then energy storage, power converter, electric motor, DC power will be supplied. If the electric motor is induction type, in that case, this energy storage, DC will be taken. Power converter will convert the DC into AC, and it will give to the electric motor. And induction motor will rotate with the AC input coming to it, and it will give the power to the transmission differential, and the whole cycle will be completed. Again, the feedback will go from the wheels and transmission to the input, that is the controller side. Now, what are the different types of power converters? So there are hardware to and software, both sides. So in the power converter, there is something called as a topology. Topology means circuit configuration. So here, there's things that are used as chopper. Chopper is a DC to DC converter. Inverter might be there. That's a DC to AC converter. PWM, pulse width modulation kind of a thing. We will see how the pulse width modulation is, where is it used and how is it controlling the power. Then resonant is there, and devices which are used for this topology, producing this chopper inverter. We are using the devices such as MOSFET. MOSFET is generally used in the MOSFET is having a gate terminal also, that is triggered, and in that triggering, for the triggering, we have to generate another circuit. So triggering circuit is there, that is triggering the MOSFET depending on our requirement. Then there is IGBT, insulated gate bipolar junction transistor, GTO, BJT, MCT. So nowadays MOSFET and IGBTs are used more. Okay. So whenever I'm talking about electronic controller, it is software and hardware. Whenever I'm saying power converter, it is devices and topology. Thirdly, when there is electric motor, that is nothing but the propulsion system. In the electric motor, you'll be finding that there is a type of electric motor, that is DC induction motor, switched reluctance motor, PMSM, permanent magnet synchronous motor, PMBM, permanent magnet, I think brushless motor, PMHM. So I think it is hysteresis motor or something. PM stands for permanent magnet. And there are different things. There are different CAD technologies. So FEM, EM, force, thermal graphics. So different things are there to judge the performance of the electric motor. So in case of electronic controller, there is a new technology VVVF. It is called as variable voltage, variable frequency. There is FOC. So in induction motor, we will study FOC, field oriented control. Transputer is a series of pioneering microprocessor from the 1980s. So nowadays, transputer are not used. Nowadays, very high sophisticated digital control system and controllers are used. Maybe DSP based controllers are also used for motor control. So this is a very important slide. This is a very important diagram. All these parts, mainly you have to explain what is 5 parts you have to explain. First part is electronic controller. You have to write about software, hardware. Second part is power converter. You have to write about devices and topology. So you can write maximum about power converter. Third thing is electric motor. You can write down different types of electric motor. So in today's lecture, we're going to see 5 types. Then there is transmission, differential, energy storage. So energy storage can be battery. And battery, there are 3 ways you can charge a battery. First one is you can charge the battery from the external source, and next you can charge the battery if it is hybrid electric vehicle. So there will be 2 storages. So there will be a generator as well as there will be a battery. So generator will be driving the vehicle as well as certain time the generator or engine that will be storing this energy storage battery. And third thing is if there is a regenerative braking, in that case from this output electrical power will come and charge the battery. So all those things we are going to see consequently, and you have to explain electric controller, power converter, motor, storage, and what is meant by transmission and differential. And another point you can explain is what all parameters you are measuring. So from the electric motor, motor speed is measured. From the energy storage, the SOC, that is state of charge, how much is the percentage charge remaining, voltage current from the battery, measured and given to the controller. Transmission and differential, yes, how much is the tilt, how much is the ratio of the drive element, all those things can be fed back to the electronic controller. From the wheels, the brake situation, the wheel speed can be taken to the electronic controller. With all these inputs, the electronic controller will take decision. It's a very smart controller. Adaptive controller is used in ADAS and all. And then it is going to tell the power converter what is the next step, how it is to be done. And all these things are highly dynamic, and within very small time, all these decisions are taken and executed and sensed and processed accordingly. Next slide, we are going to see, which is called as factors affecting electronic propulsion. Very important slide. So the device, the choice of electric propulsion system for EVs and HEVs mainly depend on several factors. 3 very important factors are explained here. So I can ask you short question. So there are 5 or 6 different boxes I'm going to show you in this slide. Slide, each box you have to remember. Only in this slide there are 5 or 6 boxes. So what is the first box? What are the factors for choosing a propulsion system? First thing is there are several factors. Driver's expectation. Sometimes driver expect a very high power car. So in that case, he is expecting huge torque, huge speed, and all those things. Some drivers are expecting normal speed. Some drivers are expecting car of not high torque because they are going to drive the car only through highway. It is not going to have any inclination or inclined road. It is not going to cross any hill. Okay, so depending on that, the design of the car or type of the car changes. So first one is driver's expectation, whether he wants a very high power car, medium, low power car, high speed, medium speed, low speed. Second one is vehicle constraints. Vehicle constraint means some car cannot have very high torque, some vehicle cannot have all the gears functioning properly. Maybe it cannot go well when there is a hill. Okay, it doesn't give proper performance on the hill. Some car maybe it can give maximum speed up to 120 or 130. Right, some car is having some decision design where the aerodynamic drag is too much. Some tire might be some car might be having bad tire. Okay, so those are vehicle constraints. And third one is energy source, whether it is diesel, petrol, or EV, whether it is hybrid or whether it is a fuel cell driven, depending on that. So all these are driver's choice. All these are choice of the person who is driving or who is purchasing the car. So this is one factor you have to understand which is affecting the propulsion system. So driver's expectation is defined by a driving profile which includes acceleration, maximum speed, climbing capability, that is gradient that it can take up, braking and range. Braking means whether it is electrical braking, mechanical braking. Range means once you fill up the tank by gasoline, how long can it go with the tank full? Or once you charge the battery completely in one charging, how much the vehicle can go. So far whatever electric vehicles and all these things are in the market, for one charging it might go to 200 kilometer to 30 kilometer as such, but Tesla says in one charging it can go to 650 kilometers. So that's a very big claim, and cars are also costly, so that is what is called as a range. What is meant by vehicle constraint, including volume and weight. So some vehicles are very heavy, it cannot take very high speed. Some vehicles are very light, so it can have high speed. Okay, so volume and weight of the vehicle depends on the vehicle type, depends on the vehicle weight and payload. Payload means whether five people are sitting inside the vehicle or one person is sitting inside the vehicle. Depending on that, vehicle performance changes. Energy source relates to batteries, fuel cell, ultracapacitor, flywheels, various hybrid sources. Thus, the process of identifying the preferred features and package options for electronic propulsion must be carried out at the system level. The interaction of subsystems. So these are different subsystems which are explained in the previous slide. The interaction of subsystems and the likely impacts of system trade-offs must be examined. Okay, so every part of the vehicle we should know how it is functioning, how they are related to the other part. That interaction is very much important for a overall performance of the vehicle. Now I am going to show you the first video, which is called as a DC motor function video. So how does a DC motor function? We are going to see here now. So this is a DC motor. Whenever I'm saying a motor, it will take some electricity from the outside. So here, as it is DC motor, this we are going to connect a battery to this, and the battery electricity will be DC current will be taken inside the vehicle, sorry, inside the motor. And motor is having two parts. One is called as the armature, which is the rotating part, and another is called as a field, which is the static part. So what happens is whenever this current is taken inside the motor, that coil is receiving, that is the field coil is receiving supply. It generates a magnetomotive force, and the armature coil is also getting the supply from this external supply, and that is a current carrying conductor. And now you have to apply Fleming's left hand rule, which says that current carrying conductor. So how the current is carried? Because we are connecting supply, electric supply externally to these two points, and they are taking the current inside and giving to the armature. So current carrying conductor means armature conductor. They are placed in a magnetic field. Now that field is electromagnet, because if you remove this source, then and there, the electromagnet will be disconnected from the source, and the magnets will not be there anymore. It will be simple coil. Okay, so whenever this current carrying conductor is placed in a magnetic field, so magnetic field is electromagnet, so whatever field we call, it is nothing but magnetic field which produces flux or flux density. So current carrying conductor placed in a magnetic field experiences a force, and that force actually rotates this shaft. What is meant by load? Very heavy weight we want to rotate. That very heavy load we put on this center, this axis. It is connected to pulley and all. Actually this is called motor shaft. So on that, with pulley arrangement, we connect the load. Okay, so that mechanical force. So what is a motor? Motor is nothing but a electrical to mechanical energy converter, and whenever we are connecting DC supply to it, it is called as a DC motor. So link of this video I will upload in this lecture. You just listen to what this person is saying. It's a 4 minutes video. I will try to explain in between. I'll pause it and try to explain. So let us see how does a DC motor function.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions: a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC power sources. To know more about it, please check the next video. Thank you.
Okay, so after that video, we are going to see what is the next is there. So we are going to see.
You can find DC motors in many portable.
We're going to see next topic, that is the types of DC motor drives. So we found that there are mainly there's mainly this brush thing is there. Brush is actually taking the external static DC supply because it is coming from a source, and there is a static voltage source, and armature is actually a rotating part. So that is a very important thing, that is who is taking this static supply to a rotating armature. So it is actually happening through a brush commutator arrangement. So external DC supply is given to the brush first, and brush is connected to the commutator. Commutator is taking the supply to the conductors. Now we are going to see the types of DC motors. So in EV, EHV, usually they require frequent start stop, because if they find that there is a traffic in between in front, or the road condition is not good, they have to stop. So this is not the case in industrial application of motors. So industrial DC motor is of one type, and vehicular DC motor is of one type, because industrial DC motor, whenever you start it, runs for a longer time. But vehicular DC motor, it has to continuously go through the cycle of acceleration, deceleration, depending on the road condition or traffic condition, or maybe there comes sudden rain. So in that case, we have to decelerate the vehicle. You have to go slow. Or if there is very good road and it is open, and we want to increase our speed, then we can accelerate. So there is a very high rate of change of torque and speed in case of vehicular DC motor. So that is a requirement motor has to suffice. So low torque, high speed cruising, very wide speed range of operation are also the features of vehicular motor. So EVs and HEVs can be classified into two main groups. One is commutator motor and one is commutator-less motor. Now, what is the main problem with commutator motor is commutator motor is connected with a brush, and the brush is connected to the commutator, and they are actually touching each other, because brush is carrying the electricity from the supply, and it is connecting to the commutator. So brush is generally made of graphite, which erodes actually whenever there is erosion between, whenever there is a friction between the commutator and brush, and there is a spark produced in the junction of commutator and brush. So that is actually a safety concern for EV, because EV spark and all this thing actually should not be there. It can be hazardous at certain time. So commutator motor, that means with commutator motor, or which is a normal DC motor, is little dangerous for EV. That's why there can be brushless or commutator less DC motor. So we will see that in BLDC. Today we'll just give you an introduction, but later on we are going to see what is BLDC and what is the drive, or what is the electronics or controllers connected with the BLDC motors. So you can find that EVs and HEVs DC motor can be classified into two groups: commutator motor and brush commutator motor and commutator less motor. DC motors are commutator motors. They are actually including series excited, shunt excited, compound excited, separately excited, and permanent excited DC motors. But yes, this is actually a primitive thing they are talking. Brushless DC motor, commutator less DC motor are also there. DC motor need commutator and brushes to feed the current into the armature, because Fleming's left hand rule says current carrying conductor should be placed in a magnetic field, and then only there will be generated a movement or rotation. So two requirements, two input requirements: the conductor should carry current, and the conductor should be placed in a magnetic field, and that magnetic field is created by the same source, that is electrical source, which is supplying the current to the armature. So whenever commutators and brushes are there in DC motor, it is a little dangerous. So, but these components require maintenance at regular interval, because this brush is continuously going to erode. So for high speed operation system with friction, the brush and commutator continuously they erodes, or they घिस जाता है kind of thing. So in addition, the winding excited DC motors have low specific power density, because we are creating electromagnet. So we are giving supply to coil which are very bulky, which are very big, and they create the magnetic flux. So this big coil and heavy coil actually they are reducing the overall power density of the motor. Hence, we can remove this electromagnetic coils and we can use permanent magnet. So instead of electromagnet, we can use permanent magnet. So these are the two modifications that is done in case of DC motor. So brush commutator arrangement can be removed, as well as permanent magnet can be used in case of electromagnet. So that's why it is called as a very advanced motor, which is called as a PM BLDC. PM is permanent magnet, so in that case the coil is gone, and brushless DC motor where brush commutator element is gone, so it will be safe because there will not be any no friction or spark generation. So we are going to study PM BLDC motor in this module only. So because of the mature technology and simple control, DC motor drives have been prominent in electric propulsion system. One very important characteristic I would like to tell you, that is DC motor has very high starting torque, and that is the main reason. So you should remember this and you should write it down, that why DC motor. DC motor is having a very high starting torque. Why so? That we are going to see in module number 3. And because of that characteristic, just for starting the vehicle, DC motor is the best choice, because initially it just gives a kind of an impulse kind of a torque, huge starting torque it produces. And it's a mature technology, since long this technology is in use, so we know about DC motor quite well. So it is a very big contender or good contender for EV and HEV application. Now you are finding here classification. It will not be asked in the exam, but you should know what are the different types of motors and drives. So with commutator motor, that means it is a conducting type of motor, or DC motor, DC conducting type of motor. So this is self-excited, separately excited. What is meant by self-excited? If field and armature both are getting electric supply from the same source, electrical source, it is called as a self-excited motor. And if for field and armature we are using two different electric supply, that is called as a separately excited motor. So in self-excited motor, if field coil and armature coil they are connected in series, it is called as a series self-excited. If field coil and armature coil they are connected in shunt, it is called as a shunt self-excited motor. Separately excited, yes, field excited and PM excited. That is field excited and permanent magnet excited. So these are two different things. What is commutator less motor? So DC motor is called as a conduction type of motor, or which is called as a commutator type of motor. Induction type of motors, that means where we are using AC type, that means AC motor, AC supply we are using, that is mainly a commutator less motor. So you are finding here induction motor, this is the first type of commutator less. Squirrel cage motor and wire wound rotor, wound rotor. So these are the two types of induction rotor or induction motor, squirrel cage type and wound rotor type. Squirrel cage is most widely used induction motor, but wound rotor motors are having a very high power. So these two, any of these two can be used in case of EV or HEV application. Remember, they require AC supply at the input. In commutator-less motor, there are very good advancements. So in synchronous machine, there is wound rotor, PM rotor, and reluctance. Okay, so we are going to see SRM motor, switched reluctance motor. What is meant by reluctance? Whatever is resistance in uh, electric circuit, reluctance is exactly like that. So low reluctance, high reluctance. Reluctance means it's the opposition offered to the flow of flux. That is what is called as a reluctance in magnetic circuit. So switched reluctance motor is there. That is actually falling in the category of synchronous. And then there is PM brushless, permanent magnet brushless, switched reluctance, PM hybrid. All these different types of motors are there. So now in consequent 4 5 slides, we are going to see all these different types of motors and their introduction. So this today's lecture is only for introduction for different types of motors and principle of DC motor. So technological developments have taken commutator-less electric motor into a new era. So this right side, induction, synchronous, PM, BLDC, all these are commutator-less electric motor. Advantage includes high efficiency, higher power density, and lower operating cost. And they don't generate spark. Spark is generally generated at the brush commutator arrangement in case of DC motor or commutator type motor. So this commutator-less motors are also more reliable and maintenance-free compared to the commutator DC motor. Why maintenance-free? Because there is a very less friction in commutator-less motors. Thus, commutator-less electric motor have now become more attractive for EV applications. Next, we are going to see induction motors. So, induction motors are widely accepted as commutator-less motor type EV or HEV propulsion system. This is because of their low cost, high reliability, and good power conversion uh, and maintenance-free operation. Because there is no brush arrangement in case of induction motor. But only a extra thing you require here, because you need AC supply. So whenever the battery is there, so from battery it is generating DC. So you need a DC to AC converter in between, which is called as an inverter. So that is a only additional thing that you have to use in case of induction motors. However, conventional control of induction motors, such as variable voltage, variable frequency, cannot provide the desired performance. So for that, we have to use VVVF, FOC, all those things we have to use. We will not discuss all those things in detail in this course, but yes, all the videos and literature will be given to you. Those who are interested, they can see what is meant by field oriented control and vector control, VVVF and all. And these are the things actually is being done at the industry. So question might be asked at your interview regarding VVVF or field oriented control. However, this EV and HEV motors using FOC, that is field oriented control, or vector control, still suffer from low efficiency at light loads. That means whenever the load is very light means vehicle is on road, which is a flat road and very smooth road. So at that time load is light. So heavily loaded means whenever the vehicle is asking for more torque, vehicle wants to cross a hill, at that time load on the vehicle is more. So, however, this EV and HEV motors using FOC still suffer from low efficiency at light loads and limited constant power operating range. Limited constant power operating range means there is a range which is giving you constant power. So, better or wider is the range, it is better. But this motors, induction motor, cannot give you wide constant power operating range. So, only for a very small range, the power is constant, and if you're increasing the speed, the torque will reduce very fast. Synchronous motor, so we will study this thing in detail. Induction motor, we'll study this thing in detail, and we'll see there are different drives. That means what are the different electronic circuits which are there to control the performance of AC motors or induction motor. Synchronous motor with permanent magnet, so there is something called as a synchronous speed. Ns is equal to 120 into F by P. It's also AC motor. So F is nothing but supply frequency divided by P is number of pole. So in permanent magnet synchronous motor, which is called as PMSM, remember all these short terms. So synchronous motor always runs with a synchronous speed. So if I'm saying Ns is equal to 120 F by P, your induction motor never runs with synchronous speed. If synchronous speed is suppose 1000, induction motor will run at maybe 950 rpm. Okay, so if synchronous speed is 1000 rpm, say, induction motor will run at 950 rpm. That means speed is slip is 5%. That is 1000 minus 950 divided by 1000 into 100. But synchronous motor, whenever I am saying synchronous motor will run always at synchronous speed, and if it falls below synchronous speed, it will come directly to zero. So either it is running with synchronous speed ns, or it will be stopped. So permanent magnet synchronous motor, the field winding of conventional synchronous motor are replaced with permanent magnets. So we are finding very important thing, that is in PMSM, field windings are not there. So field coil actually it eats up quite a lot of power while converting that electrical energy into magnetic energy. So that problem is solved here by putting permanent magnet. So whatever electricity supply is given to the motor, all the thing mainly is there to create the stator field or something. So in this case, we are not actually giving any supply directly to the stator. So all the electricity is given to the rotor itself. So hence conventional brushes, brush, slip ring, field copper loss, all are eliminated in this type of motor. PM synchronous motor, PMSM, I told you, are also known as PM brushless AC motors or sinusoidal fade PM brushless motors because of their sinusoidal AC current and brushless configuration. So all different types of losses are minimized in PMSM and efficiency is increasing. So the brush loss, commutator loss, field loss, all those things are minimized in case of PMSM. Since these motors are essentially synchronous motor, they can run from a sinusoidal or pulse width modulation supply without electronic commutation. So PWM is required. So extra another circuit is required to generate PWM, which will be the input to this PMSM or synchronous motor with permanent magnet. When PMs are mounted on the rotor surface, they behave as non-salient synchronous motor because of permanent permeability of PMs is similar to that of air. So permeability is a concept which is coming with magnetism. So what you are finding is permeability of PM is similar to that of air. Synchronous motor with permanent magnet, that means PMSM discussion is going on. So with those PMs buried inside the magnetic circuit of the rotor, the saliency causes an additional reluctance torque which leads to the facilitating a wider speed range at constant power operation. Previously, in case of induction motor, we found that constant power region was not very wide. But in case of synchronous motor, how it is happening, you don't worry. You don't have to explain, but at least you can remember that constant power region is wider in PMSM compared to induction motor. By abandoning field winding, that means the field winding is cut because it is permanent magnet itself is producing the flux. By abandoning field winding or using PM while purposely making use of the rotor saliency, synchronous reluctance motors are generated. So these motors are generally simple and inexpensive. Mainly you have to remember what are the advantages. So how exactly it is produced on construction, I don't think you can remember. So don't worry about the construction. Only know what is meant by synchronous motor, that is it runs with synchronous speed. What is meant by permanent magnet? Why permanent magnet? Because we are removing the field coils, stator coils, and that is actually saving a lot of copper loss, that is saving a lot of power, that is actually reducing the bulk of the motor. These motors are generally simple and inexpensive but with relatively low output power. So for smaller EV, smaller vehicles, this simple and inexpensive synchronous motors can be good. So similar to the induction motor, these PM synchronous motors also use FOC for high performance application. Because of their inherently high power density and high efficiency, they have been accepted as having great potential to compete with the induction motor for EV and HEV application. So far we have discussed only two types of motors. One is DC, another is induction. And in induction, we are having two types. One is simple induction motor. It can be three-phase, single phase, or it can be synchronous motor. So synchronous motor is also an induction motor, and normal induction motor is can be one phase or three phase. But compared to normal induction motor, it is better to use synchronous motor type induction motor because of their inherently high power density, high efficiency, and they are having great potential to compete with the induction motor for EV and HEV application. And one very important thing is FOC for high performance application can be used in series with synchronous motor. Now we are coming to the type of motor which is mainly used nowadays very heavily for our EV application. So by virtually inverting the stator and rotor, so where stator was there, generally stator is static and rotor is rotating. But in case of brushless DC motor, what we find is wherever we are giving supply, that is not rotating, that is static. So actually we are inverting the stator and rotor part. And that actually this is commutator less and there is no permanent magnet. So permanent magnet brushless, sorry, there is no field coil, so it is a permanent magnet brushless DC motor. It should be noted that the term DC may be misleading. It is not actually a DC motor. They are fed by a rectangular AC. So when we study chopper, we will find how to produce pulsed DC. So it is called as a pulsed DC. So from pure DC, it is generating a pulsed DC, but we cannot call it AC because it is not AC. It is called as a pulsed DC. That's why what somebody says is that yes, we cannot say brushless DC motor is a DC motor because supply is rectangular AC or rectangular pulses. The most obvious advantage of these motors is that the removal of brushes, which makes them lighter And not only lighter, because of brush commutator arrangement, there is a friction and there is a spark generation. When you are removing the brush commutator arrangement, spark generation will not be there, and it will be more safer. Another advantage is the ability to produce large torque because of the rectangular interaction between the current and the flux, because input given is rectangular pulses. Moreover, the brushless configuration allows more cross-sectional area for the armature winding, since the conduction of heat through the frame is improved. An increase in electric loading causes higher power density. How is it happening? Don't need to remember, just you mention that a brushless DC motor is having higher power density. It is more safe. There is a better cross-sectional area for the armature winding. All those things you can say. Unlike the PM synchronous motor, this PM BLDC motor generally operate with shaft position sensor. So whenever there is coming some advantage, better advantage, it is coming with some extra accessory. Induction motor, we found induction motor is not using brush commutator arrangement, but we have to connect an inverter there. In case of PM BLDC motor, it is necessary to know what is the position of the rotor. In that case, we need a position sensor. So with the rotor of this PM BLDC, we should connect a position sensors, okay, on the shaft of the PM BLDC motor. So we will study this thing in drive section, brushless DC motor drive. We will see how this position sensors are actually affecting or doing some favor for proper control and rotation of brushless DC motor. Recently, sensor-less control technologies have been developed in the Power Electronics and Drive Motor Laboratory of Texas A&M University. Last slide and last motor we are going to discuss. This is also a very important type of development. It is called as a SRM motor, or which is called as a switched reluctance motor. So they have considered potential for EV HEV application. These motors are direct derivatives of single stack variable reluctance stepping motor. So I think you have heard of stepper motor. Stepper motor is used in printer. Stepper motor is used in robots. So wherever we don't want total rotation or continuous rotation, but we want angular position control. So maybe the hand should move from 0 degree to 30 degree robot arm. In those places we are going to use this kind of thing, which is called as a that which is called as the first type which you mentioned, which is called as a stepper motor. So this switch reluctance motor is type of a kind of a variable reluctance stepper motor. So they have definite advantage of simple construction, low manufacturing cost. That is another thing. Outstanding torque speed characteristic for EV and HEV. Although they process simplicity in construction, but their design and control are complex. So how to design this kind of things and how to control this motors SRM, it is a little complex because of the heavy saturation of pole tips on the fringe effect of pole and slots. Their design and control are difficult and subtle. So fringing effect is, suppose if you see kind of a horseshoe kind of a magnet, so there is a north pole and south pole, and between that air is there. So as long as the flux lines are passing through the magnet, that is a horseshoe magnet, they will be all the flux lines would concentrate and stay within the magnet because they want to follow the least reluctance path. And whenever the flux lines are passing through the magnet, the opposition offered to the flux is least. But whenever it comes to the tip, that means there is an air gap between the poles north and south, they will bulge out. Okay, so the this thing, the flux lines will bulge out, and then again they will get concentrated whenever they are going from north to the south. So inside the magnet they will be concentrated, but outside the magnet, whenever they are passing through the air gap, at that time they will bulge out. So this process is called as a fringing. So that is one of the problem in case of switch reluctance motor. But anyways, traditionally SRM operate with shaft sensor. So as you found in case of BLDC, in case of SRM also there is a shaft position sensor, which detects the relative position of the rotor to the stator. This sensor are usually vulnerable to mechanical shock and sensitive to temperature and dust. So without shaft sensor, we cannot operate BLDC or SRM. Okay, so sensors must be there. But these sensors are usually vulnerable to mechanical shock and sensitive to temperature and dust. So they might go bad. And if they go bad, we don't know how to start the motor, because this shaft sensor are generally required at the starting of the motor. So when the motor starts rotating, at the time this shaft position sensors are of no use. But the shaft position sensors are used only in case of starting of the motor, and they might go bad in dust, heat. So we have to continuously do the maintenance of shaft position sensor. Apart from that, all other characteristics are good. So therefore, the presence of position sensor reduces the reliability of the SRMs and constrains some applications. Recently, so this is again another development by Texas A&M University. Sensor-less technologies have been developed in the power electronics and motor lab. Again at a Texas A&M University. That means it does not require shaft position sensor, and without shaft position sensor also they have designed SRM. So these technologies can ensure smooth operation from zero speed to the maximum speed. So lowest speed to high speed control of EV or HEV without any shaft position sensor. This is not possible. So this was the introduction of all the different kinds of motors which are used in case of EV or HEV. We will start with the construction, functioning, characteristic of DC motor and DC motor based chopper circuit in the next class. Thank you.